So another class of problems that we will be dealing with, another popular class of problems, involve basically inference on the whole graph. So one example is graph classification. In the graph classification problem, for instance, we want to predict solubility of some molecule. And we're representing a graph using a molecular graph. We're representing a molecule using a molecular graph. And we say that, for instance, we want to see if this is soluble in water or not, right? So actually, the image is different. So another example is that we would like to see if the molecule is toxic or not. So we have two classes. We would like to see which category this molecule belongs to. So for that, we are again gonna use a linear mapping. But this time, the difference is that we're gonna use the graph level feature representation instead of the node level. We call that ZG. And we're gonna learn some W. You can think about it as an additional layer at the end of our network, which is mapping the ZG, the graph level feature representation, into a vector of scores. And let's say that we have C different type of categories. For the toxicity problem, it is two classes. So it is of dimension D times C, which is mapping a D-dimensional representation into a C-dimensional vector. So similar to the previous problem, again, we have this Y bar, we have this vector of different scores. We want to normalize it. And for that, we use softmax. And after normalizing that using softmax, we'll have a vector. You're showing that with Y bar. And that's going to be the probability of this molecule, this molecular graph, belonging to each of either of these two different categories, or as C different categories in general. So this time, we're again going to use maximum likelihood estimate. We're going to minimize the log of the probability of this true label given the representation Z of the molecular graph. But our training data is a set of molecules instead of a set of nodes. And we're going to show that using calligraphic G. And this is a data set of different molecules that contains basically a set of molecules for which we know the true label. So let's say that, for instance, we have different molecular data sets, zinc, which is contained of molecules which have a maximum size of 39 or 38. And then we have QM9, which is a data set of smaller molecules which have a maximum size of 9. You will see that in your third homework as well. So again, like the previous problem, we are gonna basically do a dot element-wise product within these two vectors. So essentially, we're gonna take the probability for the true class, and then we're gonna basically plug that into our loss, and we're trying to maximize that. Second interesting problem for the graph level tasks is graph level regression. So graph level regression is essentially similar to the classification problem, except for that in the output, we don't want a set of scores. We want a single real value, which is representing, for instance, in the basically molecular graphs, it's in the representing a property, a chemical property of that molecule, right? So now, for instance, some energy of that molecule. So now our W is mapping our graph level embedding into a single value. So essentially our W is a vector here, and this is of dimension D. So we can multiply that with ZG. Now, the difference now here is that we are not going to use a softmax or anything like that. We're just going to take that prediction, that output Y bar. So our loss function now is defined using basically, for instance, mean squared error. We're just finding the L2 norm, squared L2 norm of the vector of the differences between the essentially, if it's a vector, but usually it's just a single value. So you can do, for instance, multi-regression problems that you are predicting, for instance, 5 properties at the same time. So your output is basically a vector of dimension 5. But here, let's say that we have a basically single value. So we just try to minimize the distance between these our prediction and the true property value for that molecule. So far, what we have said is that we're gonna map that embedding using a single basically weight, right? We're use a linear mapping in order to map that into some prediction. But in principle, we can use any deeper, essentially neural network in order to do this mapping. Given the embedding, we map that into the prediction. The only thing that you need to consider is the nonlinearity at the last layer. So for instance, if you're predicting the property, some property value that can be both negative and positive, and then in the last layer, you add a ReLU, that is essentially going to say that if it's negative, it's going to go to 0. So you won't be able to predict something valid using that. Or if you're doing some classification problem, you need to basically you make sure that you're using a softmax at the end, or if it's a 2-class classification, you need to use a sigmoid essentially. So last topic that we're gonna talk about on basically training graph neural network is the computational efficiency of our basically implementation. We have defined our basically equations, our GNN equations, our propagation rule on a node level so far. One approach to improve this is by implementing graph level equations. So, for instance, for the GN approach, our equation was gathering all information from the neighborhood, and it was trying to add that into our previous state of the node. And it was basically, it added some parameter epsilon, which was showing the importance of our target node in basically comparison to the messages that it's receiving from its neighbors. So now we can rewrite this in equation format, for instance, in the basically graph level format equation. For doing that, we're saying that we can, instead of summing over all neighbors, we can use the adjacency matrix. And in order to add the node itself, we can just add some self-loop, which is represented using an identity matrix. But this identity matrix needs to be multiplied by that epsilon parameter that we're using now, right? So we are going to say that 1 plus epsilon times I, which is going to show the importance of the target node, plus A, and then the whole thing is going to be multiplied by a vector H, which is just our node embeddings stacked on top of each other. So H is going to be a D times V, essentially, matrix. And then to update that in GN, we're using some deep, basically neural network as our update step. So let's say that we wrote this and we implemented this. This has some drawbacks. For instance, if your graph is very large, your matrices are going to be very large, and then you might just run out of memory in some cases. So that's one problem. You don't want to just write it as a whole matrix. The other problem is mini-batching. But if you want to divide this into different mini-patches of nodes and you perform neural message passing on different mini-patches, in each mini-batch you only select some nodes, then you will have some difficulties, right? You won't be able to do that using this matrix representation. So that's the second problem. For these issues, basically we need to be careful in the basically case where we are using basically matrix representation, matrix basically graph level equation to implement our basically neural network propagation rule. So one approach another approach to improve the computational efficiency of our model is by mini batching, as we said before. And in mini batching, we are just gonna say that we are gonna divide our graph into different basically subset of nodes. And then at each step, at each basically batch, we're gonna go over one of these mini batches. And then each epoch, each basically training iteration is gonna consist of different, basically going over different mini batches in the graph and training, basically performing our neural method passing over this. But we need to be careful about this as well. There are some issues, there are some caveats. One problem is that you need to, similar to the neighborhood sampling approach, when we only perform our neural message passing on a subset of nodes, for some of the nodes, you're going to lose some of the neighbors. And losing some of the neighbors means that you're going to lose some of the information that you're gathering in the aggregation state, right? So that's something that you need to be careful about. For that, changing the mini batches over different iterations might help, right? Another problem with this is that when you select a mini batch, there is no guarantee that this mini batch is just a connected set of nodes. Maybe it's disconnected, right? Because you remove some of the nodes that are in the graph, you remove the edges that are incident to those nodes, and then that basically results in a mini batch of disconnected nodes. So you need to be basically careful of how you're selecting your mini batches as well. So to date, we went over the training procedure for the graphs. We basically said that different levels of task. We have two things that we need to basically care about. We need to care about our training data. We need to care about our loss function, and we need to care about the way that we are turning our embeddings into predictions. So we looked at node classification problem. We said that we're using node level embeddings in order to basically as our input, and then we have some linear mapping that maps these embeddings into predictions over different classes. Then we said that the data set for node classification contains three basically types of nodes. One is the training node, for which we know the labels, we know its connections. A second set of nodes are transducted test nodes, which we don't know the node labels for these, but we know that they exist and we know how they are connected to the rest of the network. And the last group of the nodes are inductive test nodes, which are not seen during training. So, for instance, the approaches that we talked about earlier, the shallow embedding approaches, cannot handle the inductive test nodes. So, then we moved to graph level classification problem, in which we were using a graph pooling in order to generate some graph level representation. And we were using that graph level representation, mapping it using some linear layer into some categories. And then we were applying some softmax or sigmoid basically layer in order to turn those scores into predictions over different categories. We had a graph level regression problem, where again, we had a weight. This time, this weight was just mapping that into our predictions. We didn't need to add any other layers at the end. And we were saying that you're going to use basically negative log likelihood. You're using basically that type of loss for graph level classification. We were using mean squared error for training our model in the regression problem. And we discussed some basically issues with computational efficiency, how to improve them by implementing them in basically graph level equations, using graph level equations, and then caveats that it had. And then we looked at mini batching, basically the graph into different nodes and the basically things that we need to care about in order to perform